Hi everyone, this is Jaffer, and I would like to take today's session to talk a little bit about refuting some of the claims made in Eric Dubay's 200 Proofs the Earth is Not a Spinning Ball. And as if you're watching this video and you've seen that, then you know that it's pretty compelling, pretty convincing. But it is based on half-truths, and it is not accurate. And some things in it might be accurate, but it is basically created to try and deceive you into thinking that the Earth is flat, which it is not. And uh, I probably plan on doing a series of sessions where I will be talking more about some of his claims and debunking them. Um, I know some people have already tried to do that. I don't have the time to go through all of those, but so I'll just be debunking them in my own way. So first I'd like to start off with is talking a little bit about um, relative motion. Now I'll try to avoid going into going into the physics and the mathematics of it. But basically, relative motion, the way it works is that you feel movement when something moves relative to you. So if you're sitting on, say, on the in the aisle seat of a 747, and someone walks past you and brushes you slightly, they do it because they're moving relative to you. But relative to the ground, you're both moving at more or less the same speed, but obviously the difference being that you're sitting and the other person is walking past you. So now if that person was still on the ground and you move past them at that speed, the collision would obviously be much more considerable. So basically what I want to try to talk about in this video is that he tries to state that if the Earth was moving, then you would feel movement, and in particular you would feel more movement closer to the equator because the movement is greater. And the fact that we don't is one of the proofs that the Earth is not spinning. So basically, it seems like the one general concept that this person is missing in all his analyses is negligibility, if I'm saying that correctly. Yes. So basically, I mean, if you were standing on top of, say, what's an example of a really big spherical object that we know? Let's say the globe at Universal Studios. There's like a real lifelike. Let's actually try to pull that up. See how big this thing is. Okay, so it's pretty, it's not something that you see walking around, like any other city. So this is one of the bigger models of the globe. So say if you were, a dog or a cat who's on this thing, and you somehow manage to get this thing to spin at, a certain speed, then maybe you would feel some movement because your size relative to the size of the Earth is, much less than our size to the relatively to the size of the actual Earth. And now then the other thing is that now in that previous scenario where I mentioned, if that dog was on this thing and this thing was spinning once every 24 hours, would they feel the movement? Probably not. But say if it was spinning once an hour, maybe they might feel a little bit. If it was spinning once a minute, they would probably feel it. So it really is all about scale and relative magnitude. So to expect, us who, I guess in scope of this scale right here, we would probably be the size of, like a flea, maybe, not even that. A flea would be the equivalent of maybe, a giant building on this scale. So, and if we were on this thing and it was spinning once every 24 hours, our chances of feeling that are next to impossible. It might be possible to do that using very sensitive and sophisticated hardware, but even then, because there's no acceleration or deceleration, well, there is actually very slight deceleration, negligible deceleration, because obviously there's nothing pushing the Earth. So whatever spin that it has, it is the result of cosmic collisions that have caused, first of all, this planet to form and for it to end up in the sun's orbit. And it just happens to be in a certain point in its kinetic life that it has all these attributes like speed, velocity, rotation, angle, and all these things. And these are, for the most part, coincidental, as science would explain, as physics would explain. The same physics that holds the aircraft up in the air, so we know that it's true physics, at least for the most part. So hopefully this sheds a little bit of light on why you don't actually feel any movement when you're on the Earth. Movement related to the spin of the Earth. You might feel other kinds of movement resulting from, plate tectonics and things like that, but you really shouldn't feel any movement no matter where you are, because of your scale to your scale of your size to let me say mass, the ratio of your mass to the Earth and the actual speed of rotation. Now, the 1,500 miles an hour speed that he claims that the Earth is spinning at around, the bigger bulge of the equator is relative to the space that it's in, not relative to the atmosphere. The atmosphere is moving with the Earth because it is held down by the gravity, just like how we're held down by the gravity, which is basically the result of displaced space. So the presence of the Earth pushes space out and compresses it around its immediate boundary. So basically the space around here is more compressed, and as I go out it starts to normalize, which is why as soon as you reach the altitude at which astronauts feel less or no gravity, it's relatively quick and sudden. So you're going up, you're still feeling the gravity. All of a sudden you're out of the Earth's atmosphere. You're probably still feeling gravity then, but they probably have to go to a certain distance at which the space starts to normalize. And there's actually still gravity here, there's gravity here, there's gravity over here. But it's much, much less in scale in comparison to the gravity that is present in the closer edge of the Earth, of the surface of the Earth. You get what I'm saying? So why do space shuttles launch the way they launch? Like, why do they, see if we can, just for the sake of it, see the side where we have Florida here. All right. For the sake of demonstration. Okay, here we go. Here we go. All right. Just say Cape Canaveral is somewhere around here. And so the space shuttle takes off. It's going to go straight up in the beginning, and then it's going to start to go sideways. And another one of the arguments that they made is that that flat earthers make is that the booster rockets, once they're done, then the space shuttle has very little to actually go off of. That may be true, but at that point the space shuttle is traveling at a very, very high speed, probably which is enough to create the projectile, to insert it into the Earth's orbit, which requires a velocity of 17,500 miles relative to the Earth. At that point, it is probably moving at that speed relative to the rotation of the Earth, so it can stay in orbit because it's pushing itself away from the Earth, and the Earth is also pushing back in. So those two forces are canceling themselves out, and which is what results in an object ending up in orbit. So basically, it that you should explain why after it goes up it has to occur, because if it keeps going up, no matter how far it goes, it's going to come, say, like, let me try to explain this with my hand here. So it would sort of pop up like that if they went straight up, and then it would reach a certain distance, and even though gravity will be very little here because it's not orbiting, it's not moving away from the Earth, or it has no force, it is going to start getting pulled back in slowly. Even though the Earth is rotating at that point, that doesn't mean that it is in that it is exuding some kind of, I think they call it centripetal force, out away from the Earth to actually keep it in orbit. So that's why it has to come up and go at a certain angle. Now, obviously, the kinematics of this would be, somewhat complex, and it would require a bunch of mathematics here to try and prove this thing, but basically that's sort of what happens. And another argument that they make is that the water around the center of the Earth should cover the land because of that rotational force and movement. So again, 1,500 miles an hour seems like a lot, but if you were to say, spray this whole thing with some kind of wet paint and spin it, say, like, I don't know, 100 rotations per minute, or, something, okay, 5 rotations per second, let's go with that. Then you would see water bulge out, that wet paint bulge out from around where the center is. Okay, but if you rotate the Earth, this same model, at a speed where it is 1 rotation every 24 hours, whatever that is per second or per minute, then you would not see any of that liquid, which is stuck to this thing, pop out. So it really is all about relative motion. So I hope this clarifies a few concepts. I'm trying to think if I can cover anything else which would help prove that. A lot of the proofs in that presentation, the 200 proofs, is actually, a lot of them, well, most of them are, not valid. So yeah, hope this was informational and useful in some way. Please feel free to comment here, and if you have any other questions, do write in, or send a message to my Google Plus user. The name is Dark Sahara, as you can see. All right, hope you enjoy this. Thanks, bye.